Okay. So, continuing, this was our layout of the degrees of freedom. And now let me take you back to the element matrices that you've computed for this case. So if you go to page 233 in the notes, okay, you will find that for element A, the element matrix was 300, okay, 0, minus 300, 0, 0, 0, 0, 0, 0 here, okay, minus 300, 0, 300, 0, and the last row was zeros, okay. And so what we do now, right, is we put in the ID array. Okay? And recall, last time the ID array contained zeros for the entries where the displacements are prescribed. Right? So in order to assemble the full system, as we discussed in the previous lecture, we need the full ID array, 3, 4, 1, 2. Okay? So note this entry and this entry, right, we actually keep the associated degrees of freedom. Right? We put it on the top as ID for element A, right? And we put it on the side like this. Okay? 3, 4, 1, and 2. Okay? And so now you see that every entry of that matrix now makes it into the global matrix, right? So specifically, this guy goes into K33, right? This guy goes into K31. This guy goes into K13, and this guy goes into K11, okay? Of course, the zeros also make it into the stiffness matrix, but there's nothing to add, okay, so we skip them. Right? Element B, right, K sub B, and here I'll direct you to page 234, equals 2, right? So here's our 4x4 matrix. This element had some geometry to it. It was rotated with respect to the XY axes. And so as a result, it's fully populated, right? 192, 144, minus 192, minus 144, 144, 108, minus 144, minus 108, okay, minus 192, minus 144, 192, 144, minus 144, minus 108, 144, and 108. Okay. Now, ID array, these are the old entries, 1 and 2, right? And then we bring back the restrained DOFs, right? And their corresponding global degrees of freedom are 5 and 6. So we put them here, 1, 2. So this is the ID of the element B, right? And then here, every one of the entries are going to make it into the structure stiffness matrix. Okay, so for example, this guy will go into K55. Okay, this guy will go into K61. Right, this guy will go into K26. Okay, and so forth. And so now if you assemble the K itself, okay, it's a 6 by 6, right? Because you have 6 degrees of freedom. Right? And so if you follow the assignment of local entries of the element stiffness matrix into the global one, okay, you're going to find that K has the following structure. Right? So 6 by 6, this becomes 492. This is 144 minus 300, 0, minus 192, minus 144. It's the top row. 144, 108, 0, 0, minus 144, minus 108. Okay. Minus 300, 0, 300, 0, 0, 0. Okay. Row 4 happens to be all zeros. 2, 3, 4, 5, 6, right? How do you see that? Well, second element doesn't contribute to row 4 and the column, right? And if you look at the row in column 4 of the first element, it's also 0. Right? And so all these zeros go and populate the global stiffness matrix. Okay, this entry is minus 192, minus 144, 0, 0, 192, 144, minus 144, finally last row, minus 108, 0, 0, okay, 144, and 108. Okay, so this is the expanded stiffness matrix. Okay? Now remember that only the first two entries, right, first 2 degrees of freedom were free. So then it's subdivided as follows, right? You take the first 2 rows, you draw the line underneath. You take the first 2 columns, you draw a vertical line. Okay? And now you have all the submatrices that you need for your analysis, right? So the top block is exactly KFF, okay, which you've assembled before, right? So this guy becomes KFD. Right? This guy becomes KDF, okay? And this guy becomes precisely KDD. Okay. All right. Again, this example is a little bit contrived, right? It's only 2 elements, 6 degrees of freedom, and 4 of those happen to be restrained. Right? So it looks like the blocks of the matrix corresponding to the restrained degrees of freedom are larger than the ones that are corresponding to free. Again, this is just an artifact of this example that we use to illustrate concepts and do things by hand. Okay, in reality, these matrices can have millions of entries, and only small fraction are going to correspond to the restrained degrees of freedom. For the most part, degrees of freedom are free. Okay. Good. All right. So then, let's carry out our analysis procedure. So first, we solve for UF, right? Let me remind you. It's going to be KFF minus 1, right, times PF minus KFD UD. Okay? Very good. Right, so UF was just U1, U2 equals 2. KFF minus 1 is the top block with entries 492, right? You see it here. 144, 144, 108. .44, 144 here, 108 there, minus 1. Okay. This guy multiplies PF. Remember, in the x direction, the applied force was 0. In the y direction was minus 9. Okay, minus. Okay, and then in our case, UD is exactly 0, right? Because we're prescribing zero boundary conditions. And so whatever KFD is doesn't matter because it will multiply a vector of 4 zeros, like this, okay? And so at the end of the day, right, we're solving the same system as we solved before, right, to give us the following set of displacements. Plus 0.004, 0, 0, minus 0.1367. Okay, so nothing changes. Okay. Right. Okay. So element state determination is as before. Nothing changes. Okay, so I'm not going to go through that. Please consult the previous lecture. And now let me just directly compute PD. Okay. Support reactions. All right. Okay. So the general expression is, right, KDF times UF, right, plus KDD times UD for this case, right? Specifically applied to our problem, right, is going to be P3, P4, P5, and P6, okay, equals 2. So I have KDF that I grab from this block here, right, which becomes minus 300, 0, 0, 0, minus 192, minus 144, minus 144, minus 108. Okay. And this goes and multiplies the two displacements that I've computed. Right? Again, very algorithmic. 0.0400 minus 0.1367. Okay, so this is this piece, right? For the second piece, right, I had plus KDD. I'm not going to write this out because UD is exactly 0. Okay, so it doesn't matter what KDD is. If UDs were not 0, as I said before, supposedly you want to prescribe some displacement in case a result of settlement, or you have some information as to how the boundary is going to move. In static problems, you very seldom see motion of boundary nodes, but in dynamic problems, okay, you typically subject the some of the nodes that are connected to the ground, to earthquake, right, loads like accelerations, velocities, displacements, and this drive the structural response. So UDs are non-zero, okay, at the end of the day. Okay, but for our problem, it doesn't matter. Okay, these are gone, and so if you do the product, okay, what you find is exactly what you'd expect: minus 12, 0, 12, and 9. Okay, and so now if you relate this back to the structure, so this was our expanded view, right? These were P1 and P2 that you prescribe, and these were P3, P4, right, P5, and P6, right? They're support reactions. And so based on that answer, P3 becomes minus 12, right? P4 is 0, P5 is 12, and P6 equals to 9. And this is exactly as in the solution using KFF only, okay, what I call the reduced system plus free body diagrams D's for to determine forces at supports. Okay, and so much simpler and obvious procedure. Okay, so let me stop here. Right. Other than that, I do recommend when you write your software that you write it for the expanded system and do the partitioning as we discussed. Okay, and a final comment I want to make. Right, if you make a partitioning like this, okay, it is very important that you first label the free degrees of freedom, right, and then you label the restrained degrees of freedom. Okay, if you randomly label them together, you're not going to get a partitioning like this with the matrix.